Fibonacci function is a classic interview question. The sequence begins with 1 and 2. For any natural number n, its value is the sum of the two preceding numbers. So if n is 1 or 2, we simply return n. But for larger numbers we apply the rule, recursively, break larger numbers into smaller ones until we hit the base case, then work our way back up. Let's test it with n equals 5. Yup, 8. This beginner solution works. Let's make it better. Until now we assumed perfect input. In the real world, user input can be interesting. We need error handling. The Fibonacci sequence requires natural numbers. If you feed it 0, negative numbers, or floats, the function would recurse forever. A disaster. So, if n doesn't pass muster, we politely inform the user and raise an error. But there's another problem. For larger numbers, this function takes a very long time. Painfully so. This recursive solution is like summoning a demon that summons 2 more demons, and each of them summons 2 more. Hell, we need more efficiency. Our Fibonacci demons are hardworking, but bad communicators. They don't check whether someone else has already done a task. Enter memoization. We'll store already calculated Fibonacci numbers in a dictionary. The function now checks if n is in the memo. If not, it calculates, stores the result, and eventually returns the final answer. Let's test with a range from 1 to 10. The first function is called 79 times. But with memoization, only 7 calls. Brilliant. This difference grows wildly with larger n. Have you heard of Big O way to measure algorithm efficiency? Version 1 grows exponentially. Memoization reduces this to linear complexity. Much better, but we're not done. Let's optimize space complexity. This refers to how much memory or mental shelf space we consume. Creating a variable is like taking a box, putting a value inside, and shelving it. With recursion, our shelves pile up quickly. Instead, let's use iteration. No memo, just 2 variables, a and b. We start the loop at the third Fibonacci number, 3. At each step, a becomes b, and b becomes the sum of the previous a and b. Imagine this like pushing a and b along the sequence. At each step a becomes b becomes the previous a plus b. Once the loop completes, we return e. Let's test it with range 30 to 40. Beautiful. We've gone from a slow, functional beginner's version to a fast, memory-efficient solution. The time needed for this iterative function grows linearly, and the space complexity remains constant. And that, my friend, is Fibonacci done right.